Good afternoon, everyone. Thank you for letting us present our work on a mechatronically redundant and reconfigurable scale autonomous vehicle. So the key motivation behind this project was to push the bounds of autonomous vehicle research and education with a modular and openly accessible ecosystem that can lower the barrier of uh, people entering into the AV space for both education as well as research. The factoids on the right support our motivation in the fact that not everyone around the globe is able to, at the current moment, get into the field of autonomous vehicles, let alone start experimenting with it on physical or simulated means. So the problem here exists because the current platforms that are used for autonomous vehicle research lack aspects in terms of their integrity, which means the platform might either offer only simulation-based testing or only hardware deployment. In terms of flexibility, not all platforms are available to change any designs that are already there in place or add any new components to it from a novelty perspective. And finally, in terms of comprehensiveness, as the table here highlights, I won't be going into detail, but not all platforms have exhaustive features that can be used by a wide variety of research groups or educators to now cater their own needs. As a solution, we are presenting an ecosystem called AutoDRIVE, which we'll be talking throughout the presentation. So the functional description and the design philosophy behind this ecosystem is, as I just mentioned, to be open source, openly accessible, and open interface for anyone and everyone to use. And the picture here depicts the architecture of the vehicle, where we have tried to highlight different subsystems according to the color codes, and the connections now highlight their interaction between each individual components. And put together, the vehicle looks something like this, where you now have all these subsystems components integrated into a system with a small footprint of just 30 centimeters, which now enables you to use this platform for both in-house, in-lab, or in-class research and education. We have tried to segregate the novelty of this platform in terms of two aspects. First one is the modular open system architecture, which enables both primitive and advanced reconfigurability. Here, the picture shows different primitive reconfigurations which are possible right out of the box when you get the vehicle to now change, add, or replace any of the existing components or subsystems. And with advanced reconfigurability, you can now tap into the core design of the chassis, for example, or the energy management systems, computation, communication interfaces, software development frameworks, sensor suites, actuators and actuation mechanisms, lighting and indicators, or any other components and subsystems of the vehicle. What's more interesting is the mechatronic redundancy. And here, for example, you have a conventional Ackermann steered vehicle designed using the same platform to now have a hardware mechanical linkage. But now you can choose to add 2 degrees of freedom joints to each of the individual wheels. And now you get an enhanced configuration space where you can do both torque vectoring for individual wheels for the drive actuators, as well as have novel steering mechanisms and study their analysis in real world. So coming to the methodology, the way we designed and developed this prototype was by adopting the very famous mechatronics V model, which helped us to co-design the hardware as well as the software components in a concurrent engineering thinking framework. And here is how we came up with the virtual prototype and the virtual model of the vehicle as well as the physical prototype. And we went ahead and performed an X in the loop testing, starting from model in the loop all the way up to vehicle in the loop, to now validate this design and perform a design optimization at every step to make sure that we meet the specified tolerances as mentioned below. Coming to the benefits and applications, this project has a huge scope. We are just demonstrating 4 sample applications. The first one being autonomous parking using probabilistic robotics approach, wherein the whole idea is to use the modular approach of perception, planning, and motion control to navigate tight spaces. In the second one, we are using visual perception to perform behavioral cloning. Third one is multi-agent intersection traversal in either a single or multi-agent learning scenario. And in the final one, we are demonstrating smart city management using over-the-air control commands from a smart city manager server. This was just the tip of the iceberg, but what we are overall proposing is a comprehensive ecosystem that has a hardware testbed for physical prototyping and testing, a software simulator that acts as a digital twin, which enhances the variability and corner case analysis, and a modular software development framework, which supports a whole host of flexible APIs and tools that can now help develop autonomous driving as well as smart city applications. Thank you very much for your attention. You are free to try this out yourselves, and we would be happy to take any questions during the post session.